coming back to multidimensional scaling, we know there are two major eigenvectors in the distances between cities. We know this because the Earth is flat. And we know this because Columbus fell off the side of the Earth when he sailed his ship to find America, right? Okay. Yeah. If this had been a big class, I would have had laughter from that, but I understand it wasn't that great. What I'm getting at is, let's assume it's in two-dimensional space. So I'm going to initialize a two-dimensional area. And you'll notice I always use 2 dimensions because I can only do 2 dimensions on a projector. But this obviously works in arbitrary number of dimensions. And let's just place some cities arbitrarily because we don't know where they go. We don't have the true map. We only know the table of distances between cities. And let's call this one New York, and let's call this one LA, and we'll call this one Fayetteville, and we'll call this one Denver, and we'll call this one Seattle, and Miami. Now that's obviously not where they go, right? But suppose we do that, and then we say to ourselves, hey, let's look at the table. Let's pick an element arbitrarily from our table. Let's randomly choose this one. And it says the distance between Miami and Los Angeles is 2,322 miles. And then we look at our data and we say, okay, was that these two? Sure. Okay. Hey, that's only 27 miles. That's not right. What are we going to do? Well, let's make them 2,322 miles. So we'll take Miami and we'll move it like that. And we'll take LA and we'll move it like that. And now they're the right distance apart.
So you just pick a random direction?
Pick a random 2 points. I didn't actually pick a random direction. These 2 points were already on this line. And I moved them on that line. The reason I did that is if I were to pick some other direction, some of my movement would be superfluous. But as long as I'm pushing them exactly on the line on which they reside, I'm making as little change as necessary in order to achieve the distance that I know needs to be there, right? Okay. Now suppose I look at my chart here and I say, hey, there's a problem. Well, there's not a problem with this point anymore, but let's pick another random one. Next, we stumble across this one. Oops. And this one says the distance between Seattle and Fayetteville should be something, right? So we grab Seattle and we grab Fayetteville, and Seattle goes down south and Fayetteville goes up north. And that doesn't feel right. But, suppose we keep doing this for a while. Eventually, what do you think is going to happen?
It's going to converge.
At some point, it's going to converge until we, the cities are going to start making smaller and smaller changes because they're starting to be the right distances apart. And pretty soon it's just going to settle, and then there's just little wigglings until they settle into the right positions. And maybe they'll never fully converge, but they'll start just kind of doing jittery movements. And the reason they'll never fully converge is because there's this, there's a little bit of stuff that can't be accounted for in 2 dimensions, right? But if they could perfectly be accounted for in 2 dimensions, then I'd expect them to actually perfectly converge and never start and settle to the point where they don't move anymore. It does make a few assumptions. If you have a big enough data set, then we're over-constraining the problem. And if the problem is over-constrained, then you're pretty sure there's only going to be one solution that satisfies everything. If you're under-constrained, then yes, there's a problem. There could be 5 solutions to it, and there's no guarantee multidimensional scaling is going to solve anything. It's just something to do. But for over-constrained problems, it turns out to be a very effective thing to do. Eventually, we're going to discover that, hey, the shape of America looks kind of like this. There's Texas, and there's Florida, and there's Massachusetts, and Maine, and Great Lakes, and there's Seattle. And oh, hey, that one city's not even in the United States. Which one's that? Is that Michigan? I didn't even have Michigan on my thing. I don't know what city that was supposed to be. Denver. There we go. Oh, and this one was supposed to be Fayetteville. I think I got Denver and Fayetteville mixed up. There you go. If you had enough cities, it would be a lot easier to see that this is the United States. And then you look at this and you say, wait a minute, that's not how the United States looks. What are you smoking, Dr. Gashler? And then you realize what's really going on is selection, rotate. We'll go clockwise 90 degrees. Hey, good enough. And then you say, oh, it is the United States. Hey. So a few things. Why did it not find the, wow, that's a crappy United States. But I did it on a touchpad, so there we go. It didn't know the correct orientation of the United States, right? Because all we had to work with was distances between cities. There's no reason to expect it would know north, south, east, and west, but there is reason to expect it would get relative locations correct, right? So if the answer were the United States flipped or inverted and rotated, that would still be correct as far as this solution is concerned, because we'd need some other information like, hey, Seattle and New York are up north. And if we knew that, we could also constrain it so these 2 points are near the top, and then it would be oriented correctly. But given enough cities and given enough multidimensional scaling, they'd settle out and go where the map goes. And I think you can intuitively see why that would work, right? Doesn't it just feel like it would work? Okay, that's fine. So turns out it does mostly work, and that's that. Oh, before I run out of time, and I only have 2 minutes left, I said I would talk about numerical stability. So there, I've introduced multidimensional scaling. Let me mention numerical stability with principal component analysis. This approach that I'm giving you for principal component analysis is really, really, really fast. It's not necessarily the most numerically stable approach. And here's why. The computation of the second principal component depends on how accurate your first principal component was, right? So if your first principal component was off by 0.00001, which is probably about right, that's probably about how accurate this thing is, then, give or take a few zeros, then your next principal component will be computed from data which had that first one subtracted, right? And if it's off by 0.0001, but the data itself is off by about that same amount, then the amount it's going to be off is kind of the square of that or something like that. So what happens is the error with this approach compounds. And when you have compounding error, then people that study numerical stability get all these bad feelings and they say, ew, I don't like this. This must be a terrible algorithm. In truth, this algorithm is bad if you're going to compute hundreds of principal components. If you're going to compute a small number of principal components, it works pretty darn well. In my experience, this has always satisfied my needs because I usually compute only a few principal components, and I don't see any reason anybody ever needs high precision on lots of principal components. If you do, well, I mean, obviously there's good reasons to need that, but for the purpose of dimensionality reduction, you only want a few by definition, or else you're not really reducing dimensionality, right? And because it's lossy anyway, you're already accepting the fact that there's going to be some unaccounted for stuff. So I don't think it's a big deal to have some imprecision. Nevertheless, there are algorithms that do a repeating process where they regress and then they go regress the other one and they go back and regress the first one with respect to the second one and they make sure they're orthonormal. And there's a whole bunch of processes that get them exactly right. But the pseudocode's going to expand from being this tiny to 10 times this long, and they're kind of a pain. Just be aware, this is not the most numerically stable approach in the world, but it is one of the faster approaches yet known for computing principal components.